Yeah, this to me is going to be hopefully a nice welcome break from the my work on the COVID-19 pandemic. I am going to refer very briefly at the end to some of the work that we've been doing and how this relates to the ongoing crisis, but it will be very, very tangential. I'm going to go back to my roots as an infectious disease epidemiologist and talk about some of the stuff that actually, as Rob said, I started off in the very early days working with him on as a postdoc back in 2003, which was quite a long time ago. Now, one of the main really areas of interest for me has been looking at the use of infectious disease models in real time. So a lot of work historically that we've done as modelers has been taking outbreaks and looking at them retrospectively. But what we've been more interested in doing, and it's extremely relevant for the current pandemic, is exploring how useful these models are in real time. So this really is then the question that I want to pose sort of throughout this talk. Can models be useful in the early stages of future disease outbreaks in the presence of uncertainty? And so in order to do this, I'm going to go on a little bit of a journey back in time to right all the way back to 2001. So a lot of the methodology that's used by our group at Warwick really was developed as a direct result of really one of the last big crises in the UK in terms of epidemiology, which was the 2001 foot and mouth outbreak. So this is sort of a standard way that we might identify individuals. Now, in this case, rather than it being humans infected, we were talking about farms being infected with a disease. So what we would try to do is classify farms in different categories. They would be either susceptible, they would be exposed to the virus, they would be infectious, or in the case of foot and mouth disease, once identified, those animals on the farms would be culled in order to try to control the disease. So the timeline of infection in the UK looked something like this. And in terms of timeline on an annual basis, it mirrors actually somewhat the current pandemic, that a lot of us were seeing peaks throughout March and into April. In terms of FMD, it entered the UK in early February in 2001. The peak occurred around about late March and early April, but it was categorized by this really long epidemic tail that actually the final case was the 30th of September, which is off my graph there. Now, at the time, it was hugely devastating. So there were over 10,000 farms affected by the epidemic, and nearly 1 million cattle and 4 million sheep were culled in order to try to control the disease. And just to put that in perspective, that's about 10% of the national herd. So that was quite a significant proportion of the livestock in the UK. So, of course, when we're trying to deal with models, we need access to data. So this just gives you an example of the type of data that we were working with in 2001, which I've anonymized with the blanks out on the map references. So each farm in the UK is given a unique reference, which is identified by its county number, what county it's in, what parish it's in, and a unique holding number. We had the location of the farmhouse, so we had a map reference for that. We had dates that the animals were reported to be infected and dates that those animals were then slaughtered. If there was information regarding the possible source of infection, this was noted in this column. And of course, extremely importantly, the numbers and species of livestock. So these were the kind of data that were going into the model. Now, the model that we developed back in 2001 and was used since then, it's evolved somewhat over the years, but very broadly, it took this sort of form. And this is sort of the non-mathematical version. On the next slide, I'm going to show you the maths that underlies this. So broadly, and again, not meaning to insult anybody's intelligence, but this is the way that it works. The risk of infection is broadly based upon how infectious your infected farm is, how susceptible your susceptible farm is, and then some kind of distance factor, because we know that for foot and mouth disease, the closer the farm, the higher the risk. So we were weighting infection based upon distance. So the maths of it looked something like this. So we could break it down into how susceptible individual species were, how many animals there were on the farm, and also how transmissible those species were on infectious farms. And the final parameter was the transmission kernel, which is effectively a monotonically decreasing function of distance, which weights the risk of infection between your susceptible and your infectious farm. So the kernel sort of looks something like that. And again, completely common sense. The closer you are, the more likely you are to be infected. And Rob will be extremely upset with me for this line, because I know this is an extremely complicated part of the process, and it took an awfully long time for us to do this. All of these parameters were fitted to the 2001 epidemic data, and that is a non-trivial process. I'm going to talk more about this later on. So obviously what we can do is, if we're doing this retrospectively, we can look back and we can say, well, how well did the models fit? So on the left-hand side here, you can see anything that's in red here was an actual infected farm from 2001. Anything that's in black is a farm that was culled as part of the control policy. This shows you here some of the errors in the data, because I don't know whether you can see my cursor, but according to the data, there's a farm here that's in the middle of the North Sea. So the data that we got were never perfect. On the right-hand side, we see a heat map, which is a prediction of the model, which shows where the model predicts that infected farms are most likely to be. And with no rigorous analysis whatsoever, just by eyeballing this, we can sort of tentatively conclude that we're getting a pretty good fit spatially to the data. Okay, so, but of course this is retrospective. So as I said at the start, we're traditionally analysing these outbreaks retrospectively. And when we look at control, we really focus upon what we could have done to reduce the effect of outbreaks. So what we do is we'll take an epidemic, we'll run our model, we'll look at how well our model might fit, and there'll of course be some uncertainty around that. And then we project that forward and we say, well, okay, what should we have done to better control it? Which in this case is like, well, how would we best target vaccination? Now that's useful in a way to do that retrospectively, but then we need to think about what we're going to do in a real outbreak. And in the event of an outbreak of infectious disease, policymakers usually want an answer to one specific question. Again, extremely relevant during a pandemic. What should we do? That's the answer that all policymakers want. Now, really what we've asked so far is, what should we have done? That's the question we've tried to answer by retrospectively analysing 2001. But what we want to do is say, well, actually, what could we do? If we had a new outbreak, how might we control that? So what we want to do is try to go from the historical use of retrospective analysis to move forward to thinking about prediction. Okay, so I'm going to give a sort of a trivial example for this, and then I'm going to show how this might relate to some of our infectious disease work. So let's say I want to say, well, what wet weather gear should I take out when I'm going for my walk today? Well, of course, it depends. So what does it depend on? Well, of course, it depends on the chance of rain. So at some point, I'm going to make a risk assessment, and I'm going to decide at what point I think I need to take a coat or an umbrella. So you may have some kind of idea, and where you draw this line is entirely based upon how risky you are. At some point, you're going to decide, I'm going to take an umbrella or I'm not going to take an umbrella. But of course, when it comes to decision making, it's not just necessarily one-dimensional. There may be other factors. There may be a chance of strong wind. And of course, nobody wants this to happen. So it may be that actually there's some part of this decision space where it's optimal to take a waterproof jacket rather than an umbrella. And I say this is a really trivial example, but what it means is you have a series of spaces whereby you can weigh up what your policy should be based upon what your understanding of risk is. Okay, so this is a trivial example, but now let's start to think about outbreaks. So when there's a novel outbreak, we have uncertainty regarding how disease will spread, which is a real challenge for those of us talking to the media about the use of our models currently, because of course they want critical decisions. And what we want to ask, therefore, is do predictions of our impact of control strategies change through time as we get more information? So I'm going to start off with a toy example of this. So what I'm going to say is, how would we try to control a new outbreak of foot and mouth disease in the UK? So And again, this is a really toy example. So what I'm going to say is we have a new outbreak, and I'm going to pose 3 alternative models. And I know that one of these 3 models is an absolutely accurate representation of the new outbreak. This is why it's a toy example. So let's say my first choice is I take the model that I used last time. And then I'm going to have 2 alternative models. And I know that one of these is true. And I've got 3 candidate intervention strategies. Now, just to highlight, with these alternative models, alternative model 1 assumes that transmission is very local, and alternative model 2 assumes that transmission happens at very large distances. That's the only difference between these 3 models. And I've got 3 candidate interventions. In intervention 1, I'm only going to cull animals on infected farms. In intervention 2, I'm going to cull animals in addition on high-risk farms. And then in intervention 3, I'm also going to cull animals on neighbouring farms. So as I go from 1 to 3, this represents more severe versions of control. But in order to decide which is the best policy, I also need an objective that I'm trying to minimise. And in this example, I'm going to use a very, very simple cost function. This is not meant to represent any kind of realistic cost. So I'm just going to say roughly in the UK, a cow is worth about 10 times as much as a sheep. I say this is not scientifically rigorous whatsoever. I'm giving an example cost function in order to determine what the best policy is to do. Okay, so what I can then do is I can run my model forward and I can determine what's the best policy under uncertainty around these 3 models. So just to explain this triangle structure here, if I'm at the corner, so if I'm at that corner of my triangle, what I'm saying here is I'm 100% sure that the UK 2001 model is correct. So if I'm on the edge, if I'm on one of the sides of a triangle, then my belief in that particular model is 0. So if I get to a corner, I'm 100% sure that one model is correct. And as I move through the decision space, I have different weights of belief in the models. So as we can see from this toy example, for the vast majority of the decision space, the optimal policy is to do severe culling. And it's only if I strongly believe that the model from 2001 is wrong, would I recommend less severe culling at the outset of the epidemic. Okay, so, and again, bear in mind, this is a toy example. But now what I'm going to do is I'm going to introduce the idea of adaptive control. So I'm going to allow my policy to update as I get more information. So what I have here is I have a phase 1 and then I have a phase 2 strategy where at the decision point, I can change my mind based upon what I observe. And what I'm asking now is what is the best phase 1 intervention if there's an opportunity to update? And then I look at my decision space again. And what I find here is if I have adaptive strategies, then this less severe policy becomes optimal for a much broader area of the decision space. So this is quite interesting that by having more flexibility, I can put in less severe culling from the onset. So I can reduce costs and then I can switch later on in the epidemic if it proves necessary. Okay, so that's a toy example, but now I want to come on to thinking about using these models in real time. So at some point during an epidemic, we resolve uncertainty, or we've resolved uncertainty sufficiently that we know what the optimal policy is. The problem here is we can't afford to wait. We have to introduce control at the start of an outbreak. And so what we want to try to do is determine the best control strategy to introduce at the start in the presence of this uncertainty. So here we have a learning phase, and then we have an optimal control phase once we have resolved our uncertainty. So again, we're going to use the same model to try to describe this. And here I'm going to focus a little bit more on trying to fit the model. So we have parameters, and this is the same, sort of the same structurally, the same model as before. We have parameters associated with infection. We have parameters associated with the susceptibility. And we have our distance kernel that weights the risk of infection between farms. And what we're going to do is we're going to fit this model, and then we're going to project it forward, but with various different options for control. And then we're going to look at how our model might predict the effect of the different controls will be at a particular point in time. So just to explain this, let's say we take a particular snapshot, then we can take our data at that time point, we can fit the model based upon the information we have up to that time point, and we can determine what our controls might be. Oops, sorry, I've skipped back. And then we can compare that to what the model would predict retrospectively. So if we fitted our model to the entire data, projected it forward from that time point, and determine what the controls should have been if I had complete knowledge. So it enables us to determine how models deal with increasing information during an epidemic. So what we're asking is, at what stage are our model predictions and control recommendations resilient to this accrual of information? So what we're ultimately doing is, in our model, is we are tracking this forward through time. So we can fit it using information early on, we can update it a week later, and so on. And then over the entire epidemic, we can look at how this affects the predictions of the different control policies as we get more information. So it's a sort of a pseudo real-time approximation of how well the model works as we accrue information. So these forward simulations would be based upon accrued knowledge that we gain during an epidemic. Now, as part of this, we need to bear in mind that we're using information on infected and susceptible premises, but also trying to determine occult infections. So trying to establish in farms that may have been infected, but are not yet detected in the data. So all of these will go into our model when we're trying to do our forward predictions. Okay. And then as a comparison, just to really see how well we do, we're going to compare this to what we call perfect knowledge. So in this situation, we're taking our parameters from fitting to the entire outbreak and then projecting it forward on a week-by-week basis. Okay, so the first thing, before I do anything else, is look at how our predictions of parameter fitting change through time. And I'm just going to give one example here, which is just the exponent on cattle transmissibility here. I mean, all the parameters have sort of similar variation. And the key take-home message from this is actually to say that in the first few weeks of the epidemic, we have extreme variation in our model's prediction of the parameters based upon early data. This is probably not very surprising. Reporting is generally not good in the first few weeks of an outbreak, and trying to fit to that, it causes a lot of uncertainty. And it takes quite a bit of time. Oh, sorry about that. That's my phone going off. I will put that on silent. It takes quite a bit of time before that settles down. Okay, so these model parameters are predicted poorly during the early stages of an epidemic. But the important thing that we want to ask is, what about control? It may be that actually my parameterization is poor, but my prediction of the optimal policy is still robust. And we need to try to understand this. So in order to do this, we're going to look at 6 competing control strategies. I'm going to look at purely culling infected farms or high-risk farms. I'm going to look at what I'm broadly calling proximity-based culls, so high-risk farms, but also either neighbouring farms or doing ring culling, or I'm going to look at 2 vaccination policies. So on the following slides, anything you see in blue is very risk-based culling. Anything in green includes proximity culling, and anything in red are broadly vaccination strategies. So let's see what it does. So firstly, I want to look at what a retrospective model would advise. So with the benefit of hindsight, if I have perfect knowledge, this shows you what the prediction of the different control policies would be in time as the epidemic progresses. And so this is really, really obvious even from week 1, that the vaccination strategies consistently win, and IP-only culling, only culling infected premises, is clearly the worst. So if I had a retrospective model, it's very clear what the best policy to do is. However, let's look at some bad news. If I then compare this to accrued knowledge, I get this situation, that in week 1, almost all of the policies predict pretty much the same impact, which is quite worrying, and comparing that with the perfect knowledge situation. So in this situation, there may be pressure on a policymaker to choose the least severe strategy, because there may be other impacts that would be lessened by going for a less severe strategy. It takes a while. It takes about 3 to 4 weeks under this scenario before the vaccination strategies again drop out as being the best policies. So we tried to work out why this might be. And if we go back and try to look at parameterization, one of the things we looked at was, okay, what do we predict regarding the risk of onward transmission? And if I look at where my model predicts transmission is in week 2, then in my accrued situation, I'm still predicting an awful lot of transmission actually in Scotland, which I don't get if I have full knowledge. By about week 3, this uncertainty goes away. And so we are predicting a lot more transmission in the early stages when we're trying to fit to uncertain data than when we get more information we just don't see. Okay, so that spatial uncertainty drives some of this. Okay, but now some slightly better news. Now, again, the statisticians on this call will be very upset with me for even considering the idea of ranking strategies based upon means. But I'm going to do it anyway because it's interesting. If I purely rank the best to the worst policy based upon the mean epidemic impact, even with this uncertainty, it's quite striking that these risk-based policies consistently come out as worst and vaccination strategies consistently win when we compare real-time versus hindsight. So that's quite interesting. And we also get this weird phenomenon where ring culling all of a sudden towards the end of the epidemic becomes better. And we assume this is because it starts to identify and target local clusters much more rapidly towards the end of an epidemic. Okay, so the conclusion of this is objectives and state clearly matter, and the preferred control strategy is very dependent upon the state of the system, but also what the policymakers are trying to achieve. Okay, so there's a couple more brief examples I want to give dependent upon time, just to sort of further hammer this home. So I want to talk about vaccination, again, extremely relevant in the current pandemic. But back in 2001, it was a question that was repeatedly asked whether vaccination would have been optimal. And there are several key questions that we need to think about. What size of vaccination ring should we use is a big one for that. What's the best policy to put in place? But unfortunately, in order to determine that, we need to think about this uncertainty. There's a lot of uncertainty about how emergency vaccination works in livestock. So first of all, what's the efficacy of the vaccine is a big unknown. How long is the delay between vaccination and immunity? And also, how many cattle do we have the capacity to vaccinate each day as part of an emergency response? In order to determine the best policy, all of these play a role. And we can use the model to try to look at this. So in order to do this, I'm going to go through another really quite toy example. So just to explain this. So let's assume that we know the following. Let's say that we know we have a vaccine and it's almost like we've picked it out of a pot and we know it's either 50%, 70% or 90% efficacy. We know that the time delay to immunity is 2, 4 or 6 days. And we know that the vaccine capacity is either 20,000, 35,000 or 50,000 doses a day. In reality, of course, the uncertainties around these are continuous, but that makes it much harder to describe in this presentation. So a toy model hopefully enables me to highlight these uncertainties. And let's say the policymakers are considering 5 possible vaccination radii, 3, 5, 7, 10 or 15 kilometers. Well, what I can do is I could basically hit this with a big hammer and I could run all these possible scenarios and then determine what the overall cost is associated with a vaccination policy under each of these conditions. So for instance, this column here would tell me, this entry here tells me the average number of cattle culled in millions if the vaccine efficacy is 90%, if there's a 6-day delay to immunity, and if I vaccinate 50,000 animals per day. So there are some key trends here that emerge. The first obvious one is that the time delay to immunity appeared to not make much difference in terms of the effectiveness of the policy, which was quite striking. The second thing was that there was a very clear dependence upon the number of doses per day. And again, this is not rocket science. It's pretty obvious that the more doses I've got, it's probably going to influence my optimal policy. So that was quite striking, that there was a shift towards larger rings being more optimal if I could vaccinate more animals per day. So what we can do is we can put this into our sort of belief triangle again, and we can try to determine what the optimal policy would be based upon our belief around our capacities. So for instance, if it's then possible to know a priori how many doses I have, I know what the optimal strategy is. But if there's uncertainty around that, I can determine what the best thing to do is. So if I'm 100% sure that I've got 20,000 doses, then 5-kilometre vaccination here is optimal. If I'm 100% sure that I've got 50,000 doses, then 15-kilometre vaccination is optimal, and so on. Okay, but the optimal strategy here is dependent upon my weight of belief on these 3 levels of constraints. Okay, so I can basically put all of this together, and I can look at what the dependence is upon these different metrics in terms of the optimal policy to do here. And I realize this is a whole bunch of triangles, and there's really a couple of take-home messages from this, that if we were able to resolve all uncertainty in the vaccine, we predict that over 200,000 fewer livestock would need to be culled in the UK, but knowing the true vaccine capacity, regardless of uncertainty around efficacy and delay to immunity, gives us a significant proportion of that saving. Most of the uncertainty in terms of the optimal policy is around capacity, which was very interesting. Okay, so I'm just going to summarize that, and then I'm going to talk very briefly about some relevant stuff on avian influenza that we've done, and then I'm going to finish. So sort of the key take-home message here is that some of the work that we've done, whilst the control actions rankings may be initially robust, there is uncertainty around these predictions, and state-specific control is crucial. So resolving uncertainty can really assist in contingency planning. Okay, so I'm going to just talk briefly about some related work we've done in avian influenza, just to highlight that this is not very specific to foot and mouth disease. So we looked at this, and of course, several years ago, we were worried that H5N1 might cause the next global pandemic. We did some work on this, looking at outbreaks in poultry in Thailand and Bangladesh to look at risk factors and try to determine optimal control policies, and particularly interested in reducing transmission risk to humans. So that was one of the key things here. Now, when we're trying to model in avian influenza, we have this difficulty in that chickens tend to get avian influenza and die, whereas ducks are generally asymptomatic. So what we're doing is we're seeing the infection in the chicken population. We're not necessarily seeing it in the duck population, but they can be silently spreading the disease quite widely. So that's one of the challenges. So what we did is we developed a model to try to determine the spread of infection between villages in Thailand and Bangladesh. So, for instance, we have infection coming in from between villages, and we had a model that was very similar to the foot and mouth disease model in structure, but with additional covariates. Now, for avian influenza, we know that water is a big risk factor when it comes to spreading the disease. So we have additional parameters that deal with things like rice paddy densities and so forth that cause additional drivers of the disease. And within a village, we model specific transmission between poultry flocks within a village. Okay, so that's broadly what the model looks like. But what we were interested in was to do a similar analysis when we look at, well, actually, how do our predictions change through time in terms of our ability to capture a historical epidemic? And I'm just going to show this for Thailand. That if we're doing a similar thing to what we did for FMD, fitting it in real time, then early on, we get extremely poor predictions of how well we can fit to the model. And it actually takes several weeks before we start to get a model that we actually can accurately fit to the data. And again, I'm not gonna go over this in any more detail because it's a very similar principle to what we did with foot and mouth disease. But it just says that the early use of these models should be taken with a certain amount of caution. If I then look at the impact of control on this, what we did was similarly, we looked at the impact of vaccination and culling and the optimal policy to do. Now, strikingly, this was quite different from the foot and mouth model, that even though we're over predicting epidemic sizes early on, we're consistently getting the best policy in terms of minimizing the epidemic as being larger scale ring culling throughout, even with uncertainty in the early stages. So that was quite striking. Okay, so the final thing I just wanted to touch on was thinking about state-dependent policies. Now, one of the things that we've tried to think about is whether we can construct a state-dependent policy where we determine the optimal policy based upon a single state of an outbreak, regardless of what happened before. So in order to do this, what we need to think about is what are we interested in? So, for example, we might be interested in thinking about an optimal culling or vaccination program, but that's dependent upon how many infected farms we have and how many vaccine doses we have, and then determining what the optimal policy is within that. So, just to highlight this, and this is an example that was carried out by one of my former postdocs, Will Probert. We did a simple sort of reinforcement learning algorithm where we tried to determine what the optimal policy would be given a particular state of an outbreak. So for this, we ran our algorithm looking at how many infected premises we had and what the current area of the outbreak was, and then tried to minimize either the outbreak duration or the total number of culled farms in order to look at minimizing, in order to look about what the optimal policy would be. And so what we can find is something like this. We can run a whole sort of decision space and then determine, for instance, dependent upon how many infected premises we have and what the overall spatial scale of the outbreak is, what the model tells us is the optimal policy to do at this point in time. And what we find here is that there's a whole area in this space where culling actions are optimal. So anything that's red is broadly a culling action. Anything that's green is a vaccination action. And then areas more towards the right when we have larger areas where vaccination starts to win. And then as we change our objective, we can see that we have a different policy that might be optimal. If we're interested in minimizing duration, then culling tends to win. If we're minimizing livestock culled, then vaccination tends to win. Okay, so I realize this has been very much a whistle-stop tour of real-time decision-making. So the idea with this is that with reinforcement learning, we could potentially have multiple objectives. So ideally, what you could do is if you have multiple objectives you're trying to achieve, you could lay these over each other, and then you could potentially identify regions of space where you have win-win situations. So places where even with a different management action, even with a different objective, the same management action is optimal. And you can have places where you have discordance, as shown in the bottom figure there. Okay, so just as a final thought, I just want to for the last minute, just look at some implications for the ongoing pandemic. Now, of course, many of us are having to go through exactly these sorts of decisions in real time currently. For COVID-19. So this just shows you a schematic of the Warwick model that's being used as part of the scientific advisory group in the UK. I'm not proposing to go into this in any detail, but I'm quite happy to talk to people who are interested afterwards. But one of the things that we've been trying to look at in the UK is assessing lockdown relaxation strategies and looking at triggering. And this is just one of the results of a preprint that we put out last month, was looking at adaptive interventions whereby we relax social distancing, but we introduce triggers. So in this situation, what we're doing is, in order to prevent a large second wave, we introduce local lockdowns when the ICU, the intensive care unit occupancy exceeds a certain threshold within regions. And you can see that this has implications, that what it does do is it ensures that the health system in any particular region does not get overwhelmed, but it gives us an extremely long epidemic tail that goes well into sort of the middle of 2021. So which suggests that we might not be out of the woods quite yet. Okay, so I propose to leave it there. Of course, I mean, I would say a lot of this work has been done in collaboration with a huge number of people. both in the UK and in the US, and also collaborators in Sweden. And a lot of the work has been done by my group in Warwick. Okay, so I propose to leave it there, but I'm happy to answer any questions.